Let's look a little bit more closely at the graphs of polynomial functions. So we have a few ideas that help us classify the behavior of a polynomial function. In particular, we talk about the degree, which is the highest power of the variable in that polynomial, and then the leading coefficient, which is the coefficient of that highest power. For example, with this polynomial, 3x minus 4x squared, remember that this is really 3x to the 1. So when we look at those two powers, the highest power is 2, so that means the degree is 2. And the coefficient of that highest power is minus 4. So the leading coefficient is minus 4. Here's another example. If you take this and expand it out, you get 9t squared plus 6t plus 1. Again, you can think of 6t as 6t to the 1, and you can think of 1 as 1t to the 0. So each of these has a power. The highest power is, again, 2, so the degree is 2. And the coefficient of that term with the highest degree is 9, so the leading coefficient is 9. Now, it's useful to be able to identify the degree and the leading coefficient because it tells you about the behavior of the graph. If your degree is even, so an even number like 2, 4, 6, 8, even at least 2, then the graph will have a U-like shape, like these two examples. So this is an even degree, power is 8, and this is even degree, power is 2. And you notice both of these shapes are kind of like the letter U. Now, if the degree is 2, then that U-like shape has a particular name. It's called a parabola. But that's only for degree 2. Notice that with this degree 8, it's still U-shaped, but it's flattened out a lot more than you get with a parabola. So if you've ever heard of like a parabolic dish, for example, in a telescope mirror or a sound amplification system, the parabolic dish has a certain curvature that corresponds to the shape of a quadratic. And if you used something that was shaped more like x to the 8th or x to the 6th, it wouldn't work right in a telescope. So the term parabola specifically refers only to the shape you get when you have degree 2. But they're still both U-shaped, and you can see sometimes the U opens upward, sometimes the U opens downward, and in order to distinguish between those, you look at the leading coefficient. So for this first example, the leading coefficient is a 1. That's positive, so the graph opens upward. On the second example, the one on the right, the leading coefficient, -3, is negative, and so that U shape opens downward. Now, that's what it looks like when you're far away, the U shape. But if you zoom in, you can get a different behavior. Both of these graphs we see here are of the same function, x to the 8th minus x squared plus 12. They're the same function, but this first picture is from very far away. Take a look at the scale. The x values go from -10 to 10, whereas on the right, we're only looking from like a little less than -1 to a little more than +1, not all the way from -10 to 10. And the height is a lot different. On the left, we're viewing from 0 to 10 to the 8th. This is scientific notation here. 1 times 10 to the 8th, that's a 1 followed by 8 zeros. That's a lot more than roughly 14, which is what we see on the right. So these are the same function, but they're viewed at different scales. It's like we're zoomed in on the right and zoomed out on the left. So when we zoom out on a an even degree polynomial, we see this U shape. But when we zoom in, there can be a more complicated behavior. In particular, anywhere the graph changes from increasing to decreasing, or the other way around, we call that a turning point on the graph. So on the zoomed in picture, we can see a turning point right here because the graph is decreasing to the left of that point, but increasing to the right of it. So this point right here is a turning point. This point is also a turning point because it goes from decreasing to increasing there. And this is a turning point where the function is increasing very slightly and then decreasing very slightly. So anywhere it changes the behavior like that, we call it a turning point. And a polynomial can have several turning points, but the most it can have is related to the degree. In fact, the most it can have is one less than the degree. So if you look at all degree 8 polynomials, the most turning points any of them have is 7, one less than the degree 8. So you can write down a polynomial of degree 8 that has 7 turning points. This one only has 3 turning points, so you don't have to have 7, but that's the most you can have. How about odd degree? So let's say you have an odd degree of at least 3, so that would be a degree 3, 5, 7, etc. Instead of a U shape, we get what we're calling here a sideways S shape, like in these two figures. So on the left, we have degree 5. On the right, we have degree 3. Now, the sign of the leading coefficient, again, tells us the behavior of the shape. They're both sideways S's, but the one on the left is mostly increasing. It's going up. The one on the right is mostly decreasing. Now, I'm being careful here with this term mostly, because this one is not always decreasing. You'll notice there's a little bit here where it's increasing. But when you zoom out, you can see that it's mostly decreasing. And you can tell that because the leading coefficient is negative. Whereas when the leading coefficient is positive, you get something that's mostly increasing. Now, again, when you zoom in, you might see more subtle behavior. So these are both graphs of the same function, x to the 5th minus 5x cubed plus 4x. And again, we're zooming in to get the graph on the right. You can see that the scale is much closer. We're only going up to about 30, not 10,000 on the y-axis. And when we zoom in, we see more squiggles here. And so we see turning points as well. There's a turning point because the function was increasing, and then afterward it's decreasing. Here's another turning point where you go from decreasing to increasing, another turning point, and another turning point. So this one in total has 4 turning points. And just like with the even degree, so this actually is always true. It doesn't matter if the degree is odd or even. The most you can have, the most turning points, is 1 less than the degree. So since this is degree 5, the most you could expect is 4 turning points, and that's exactly what we got. Now, an even degree polynomial, because it has that U shape, it's guaranteed to have at least 1 turning point, whether you're opening up or opening down. You're always guaranteed to have at least 1 if you're looking at a polynomial with even degree that's at least 2. But you can have an S-like shape that has turning points, but you can also have an S-like shape that's always increasing or always decreasing. So even degree is guaranteed a turning point, but odd degree is not guaranteed to have a turning point.